Today we're going to be doing something called Riemann integrals. Riemann integrals, or more, that's a very precise term. Maybe the more general term, the more familiar one is called definite integrals. So remember a couple weeks, maybe last week, we did indefinite integrals. Indefinite integrals were just like the collection of antiderivatives. And now we're going to talk about definite integrals, which is something more concrete. Okay. So let's think back to what we did last time. We were talking about area, right? How do we define the area? How did we define the area? Does anyone remember? What was the area? If I gave you a curve and I said, find me the area under that curve, how do you do it? It may give you a function variety.
It's the endpoint approximation at the end of which is infinity.
Yeah. So you take you take the endpoint approximation, right? And 2, you let n go to infinity, right? And that, whatever number that is, that's what we call the area, right? How to find the area, right? This is how we define the area. Area is the number that you get for like how to define. Okay, and I want to ask you a question about this. How do you so the nth right endpoint approximation? Does anything about this seem unnatural or sort of arbitrary? Like, maybe it makes sense, but okay, we're going to take integrals, and then we're going to take the right endpoint and make these rectangles, add them together, and let n go to infinity. Right? Does anything seem sort of arbitrary? Like, why did you make that choice? Yeah.
Why are we taking the right?
Why the right endpoint? Right? Why the right endpoint? Why not the left endpoint? Why not the midpoint? Why not why not allow the person to take just some sort of random point inside there? Okay. And so that's actually what we're going to do. That's actually what we're going to allow today. So the first thing we're going to talk about is some sort of generalization of the right endpoint approximation. So the first thing is Riemann sums. Sort of generalization of the right endpoint approximation. So it will basically be just the same idea, except we're going to allow you to choose whatever point you want. So given a function f, you have some function on an interval. Let's say like this. Say you have a function on an interval. Sorry to make a big all this. 2, you have a uniform n partition of AB. That is, you've divided AB into n subintervals, just like last time. You divide the base into n subintervals, and these are the endpoints of the intervals, right? Where this is A and this is B, and the change x. The change in x is b minus a over n, right? So you have AB, you've divided it into n parts, where the endpoints are x0, x1, x2 up to xn. Right. So you have a uniform n partition. Over talking it. And 3, you have a choice of points. S1 through S sub n. Okay. Where Si is in the ith subinterval.
Explain that again.
Choice of points?
Yeah.
So I haven't explained it yet. let alone. Okay. So what I mean by choice of points is that for each interval, you're allowed to choose a point inside that interval. Okay. So that would be our choice of points. So like you say, I'm going to choose this guy, and this guy will be my S1. This guy will be my S2. This guy will be my S3, etc., etc. This guy will be my Sn. Then the Riemann sum of f on AB based on let's call this choice of points capital S sub n, based on this choice of points is just the sum of f evaluated at each of those points times the width of the interval and summed over all intervals. Okay. Let me just do a concrete example of what I mean by Riemann sum, and that will make all this stuff, I hope, completely transparent. Okay. So here's an example. Here's an example of a Riemann sum. Suppose we have, say, the sine function. Okay. Suppose you have f of x is the sine function. And we're going to take the sine function on, say, 0, 2 pi. Okay. And then we say, okay, let's take, let's let n be 2. So we're going to divide this thing into two equal subintervals. Right? So here's our partition. Right? Our partition is 0, pi, 2 pi. Right. And let's say, let's choose sample points. So our choice of sample points will be, say, I don't know, pi over 2 and 3 pi over 2. No, pi over 2 and, say, 2 pi. Pi over 2 and 2 pi.
Is that arbitrary?
Yeah, I'm just making it. Okay. So choice of sample points is sort of up to you. Okay. Then the Riemann sum for sine x, based on the above choice of sample points is just going to be the function evaluated at pi over 2 times the width of the interval plus the function evaluated at the other choice of sample point at the next sample point times the width of the interval. Okay, and so you get, in this case you get 1 times pi plus 0 times pi. So you get pi. So this thing here is a Riemann sum.
And that's the area.
It's an approximation of the area. It's again sort of like a guess, an initial guess for the area. Except this time we didn't choose the right endpoints. We chose this guy, and you see what happens. We get the area of this rectangle plus the area of this very flat rectangle. Okay. Right. So it's just another way of giving an approximation of the area. The only thing is that we don't say that we always have to take the right endpoint. Right? You can take whatever point you like. Okay. So it's almost the same thing as the nth right endpoint approximation, as the second right endpoint approximation, except you're free to choose whatever point you like. So you make some choice of points, and then you get a value based on that choice of points. Okay. Right. So that's all we're saying here. You take some. I'm not sure if people are following. Are people following? I don't know.
Yeah.
Okay. So you take your function. You divide the base into n subintervals. You choose points in the subintervals, and then you evaluate the function at those intervals multiplied by the widths of the base, and then add up the areas of those rectangles together. And that thing is called a Riemann sum. Okay. So the nth right endpoint approximations are Riemann sums, but the Riemann sums are a much wider sort of thing than the right endpoint approximations. The right endpoint approximations are specific examples of Riemann sums. Questions?
Why don't you do the limit as n goes to infinity?
We will. Right now, this is just to get the term Riemann sum out there.
Okay.
Yeah, Victor.
For this one, if the choice of sample points had been pi over 2 and 3 pi over 2,
yeah.
Would that just kind of cancel out?
What would we have gotten, right? So if we took a different choice, so notice if we sample at pi over 2, 3 pi over 2, the Riemann sum, the new Riemann sum is 0, right? Will be 0.
So you don't take the absolute value.
You don't take the absolute value. Yeah, that's last time we mentioned that what we're interested in is a signed area. So actually we're considering this is a positive area and this is a negative area. And actually 0 is a good approximation. In fact, it's perfect, right? We're lucky. If we'd be lucky if we did that, because that actually is the signed area. Yeah, Mariah.
If endpoint approximation is like an example for Riemann sums, then what are the endpoints for that? Is it just the partition?
What are
the sample points? Sorry.
What are the sample points? The sample points for the right endpoint approximations are all the right endpoints, right? So they're actually the x1, x2, blah blah blah.
Okay.
Right. Okay. You notice that based on your choice of sample points, you're going to get different numbers. Okay. So that is, so I'm going to make it clear here. Based different choice of sample point results in different choices of sample points result in different values. Okay. So okay. So maybe I'll do a no. Okay, actually, I will do an example. Okay, so let me do an example. Okay, so actually, this is an example I was thinking to do last time, but didn't have time to do it. Okay, oops, nope. Ignore what you just saw. Sorry. Okay. So let's write down. So maybe this is an exercise. Here is x squared. Write down the nth right endpoint approximation for this area, for the above area. Okay. You should be able to do it. Presumably you did something similar in your homework. Write down the nth right endpoint approximation for the above area, right? So you're going to remember that you'll figure out what the delta x is. The delta x is going to be 4 over n, right? You figure out what x sub I is, right? X sub 0 is 2, right? X sub 0 is 2. X sub 1 is, well, I shouldn't give it all away.
Is the interval 2 to 6?
2 to 6, yeah. Between 2 and 6. Okay, so what is it? So let's go on. How do we figure out, right? What's x of 0 is 2, x of 1 is 2 plus 4 over n, right? And etc. X of I is going to be 2 plus I times 4 over n, right? In general, x of I is going to be 2 plus I times 4 over n, right? And so what's the endpoint approximation? Well, you take your function and evaluate it at the endpoint. What should I write here? Anybody? Ryan, yes.
Oh, f of 2 plus I 4 over n quantity times 4 over n.
Sum between I 1 to n. Right? You take your function, right, which is the squaring function. If you want, maybe it's actually just like this. Right? You take your function and you evaluate it at the right endpoint. Right? What's wrong with it? Everything.
I'm confused about what the x naught, x1 thing is.
Oh, these are the partitions, right? Remember, you divide your base into n pieces,
right.
And we call this thing x0, the first point x1. These are all the minus 1, right? These are the points from your partition.
And then we figured out that our like skip over is 4 over n.
Mm-hmm.
And
Right.
then where does that I come in?
So, the first to get to the first one, we add on 4 over n, right?
Yeah.
To get to x1, you move over 4 over n. To get to x2, you add on 2 times 4 over n. To get to x3, you add on 3 times 4 over n. To get to the ith point, you add on I times 4 over n.
Oh, okay. All right. Thank you.
Okay. Okay. So this is the nth right endpoint approximation, right? Right. So that's it, right? You end up with if you write it out, you end up with summation, right? You know, multiplying this, you end up with.
Is it 8?
What? 4 plus 16, 16I over n plus 16I squared over n squared times 4 over n. From I equals 1 to n. Right. Just squaring this thing here. Madeline.
So does that 4 over n that's on the outside, does that distribute to all of them?
Yes.
Okay.
Right. That's how, yeah. That's multiplication.
Yeah, I didn't know, like, in terms of notation, if it was, like, all of that was in parentheses and that was outside, or, like, if it was just like the last term.
Yeah. No, I mean, it actually doesn't make any difference, but remember, you're taking the heights times the widths, the height of the rectangle times the width of it, and then adding up all these things together. So it is inside, although in reality, even if you pull it outside, it doesn't matter, because you're multiplying every term by 4 over n anyway. So you could leave that 4 over on the end, 4 over n outside or inside, in fact. Yes, in some sense. I'll talk about it later. Okay. So this is the right endpoint approximation. What if I asked for the left endpoint approximation? What if I asked for the left endpoint approximation? How would I fix this thing up here? Go ahead.
I'm wondering if you would, instead of having 2 there, start with 6, since it's the end, and then subtract I minus 4 over n.
Oh, cool. Yeah, that would work. Yeah, that's not at all how I was going to say it, but yeah, that's definitely going to work. Yeah, Victor, yeah.
I'll just start at I equals 0.
Could start from I equals 0 and go to n minus 1. That's also a way to do it, right? Another way to do it is just to keep the same indices and use I minus 1, right? Which is the same thing as what Victor was saying, but completely different from what Gwen was saying. Yeah. So yeah, all those things will work. Okay. Yeah. Okay. So
Why is it minus 1? If you do like from 0.
Well, because I don't want to get the last point, right? In that case, right? If this is 2 and this is 6, right? I only want to evaluate my function at the left endpoints, right? I never want to get to 6 itself, right? But if I take all the way up to n, I'm going to get 6.
Okay.
Right? I'm going to get that last guy. I actually want to stop at 6 minus 4 over n. Right. Okay. So that's right. That's the left endpoint approximation. You can write as this: I equals 0 to n minus 1, 2 plus I, 2 plus, and then just the same thing here, right? 4 plus 16I over n plus 16I squared over n squared, 4 over n. Okay, so those two are both Riemann sums for this area. Okay. Both of these things are Riemann sums for this area. It's just that we've changed our choice of sample points. Okay. Okay. Any questions so far? Questions? Okay. So now we get to the key definition, and this is the hard one. Okay, this one confuses people a lot. So, so put on your thinking caps. Okay, so if the limit of Riemann sums exists as n goes to infinity. Okay. So, right. So you have something like this. You partitioned it into endpoints. You've made a Riemann sum. You partitioned it into, you partition it finer. You make another Riemann sum, and it turns out that this limit exists no matter your choice of points. Okay. So like one person goes into a room and says, I'm going to choose my own points. Blah blah blah. I choose my points according to some rule that I make up. Another person goes into another room, makes a choice of points that person makes up. Okay. And then lets n go to infinity. Okay. And it turns out that no matter what choice of points they make, they always end up with the same number as n goes to infinity. Okay. If that happens, if that limit exists, no matter what choice of sample points, then we call the function f integrable on AB. So you start off with some function f on AB. So if that limit exists, no matter how you choose your sample points, then we're going to call the function integrable. Okay. And we write this thing, that limit. We write this thing which is read, the definite integral of f on AB. This thing here is called the definite integral of f on AB. Yeah, Mariah.
Can you say again why it's definite versus indefinite?
That's just the term. I'm not really sure why we call it that. But this one's called the definite, and the other one's called the indefinite. I mean,
Is it because there's like a range?
maybe because it's on a definite range,
Okay.
and then the other one is just talking about the the antiderivatives.
Okay.
Yeah, that seems likely. Okay. So this is what we call this is what is called an integrable function. Okay. And let me put in a theorem somewhere. I'll put it up here. Theorem: if f is continuous, then it is integrable. So in particular, this function that we were looking at before is continuous. So whether we take the right endpoint approximations or the left endpoint approximations, as n goes to infinity, we should end up with the same number. Okay, we're going to end up with the same number, no matter. In fact, even if we took sort of random points inside each subinterval, we're still going to end up with the same number as n goes to infinity. Maybe along the way you're not going to have the same number, but when n goes to infinity, it's all going to turn into the same number. Okay. As long as your function's integrable, and if it's continuous, then it is integrable. Okay. So let me think. Do we have time to see that this happens?
Yes.
In this case, we do. Mariah says we have time to see that this happens. Okay, let's find out. Okay, so here are two. Here is the right endpoint approximation, and here is the left endpoint approximation. Okay. Yeah, one was based on this rule: choose always the rightmost point. This one was based on the rule: choose always the leftmost point. Okay. So let's see that. Let's see that this happens. That the limit of that the limits agree. Okay, so what happens as n goes to infinity when you take the right endpoint guy? Let's take the limit as n goes to infinity of summation. What do we have? 16 over n plus 64 over n squared times I plus 64 over n cubed times I squared. Because I goes from 1 to n. So this is the right guy, and then we'll see what happens with the left guy. Okay. Okay. So I'm going to do these in pieces. I'm going to look at here we're going to go from I from 1 to n. I'm going to do these sums in pieces. I'm going to take the sum of the first terms, and then the second terms, and then the third terms. Okay. Right. You can you've got these 3 terms, and you can take all of their sums, or I'm just going to take the first terms and add them all together, the second terms and add them all together, and the third terms. Let me write it out. Okay. So I'm taking the sum over 16 over n, the sum of this, plus the sum of this. Okay. Now, I've got 16 over n, and I add it to itself n times, right? So I get 16 over n plus 16 over n plus 16 over n plus 16 over n times. So what do I get?
16.
16. Right? Okay. Now for this one, I have 64 over n squared times 1 plus 64 over n squared times 2 plus 64 over n squared times 3, etc., up to n. So I've got 64 over n squared times 1, the sum of 1 plus 2 plus 3, well, up to n. Right? Well, what's that? Anyone remember?
N times n plus 1 over 2.
Very good. N times n plus 1 over 2. Right? So, n plus 1 over 2. Everyone all right? It's fun? You know this one, right?
Yeah, I know.
The plus,
I
the
don't
parentheses.
understand.
Yeah.
When you're approaching infinity with n, like, why were you?
Oh, I haven't let n go to infinity yet.
Oh,
Sorry.
okay. You're just finding the sum of each one.
I'm just finding the sum of each one. Sorry.
Okay.
It was wrong as written.
So what do you do with the n when you're finding the sum? You just leave it there?
Yeah, it's just this term just multiplies each of the i's, right?
Okay.
So when I is 1, I get 64 over n squared times 1. Then I get 64 over n squared times 2. And then I add on 64 over n squared times 3.
So why did you take out the n on the first one? The 16 over n.
It's the same thing. I have 16 over n, and then I have 16 over n again. There's no I here,
Yeah.
so all I get is 16 over n plus 16 over n plus 16 over n times. So if I get n 16 over n's, well, that's 16,
Okay.
right? Because n times 16 over n is going to be 16. Okay. Next one, we get 64 over n cubed times the sum of I squared. right? The sum of I squared, I never remember. What is it? Ria, help me. N plus 1, 2n plus 1 over 6. Thank you. Okay.
Quick question.
Yes.
We only have the three numbers, I
Mhm.
mean the 16 over n and 16 over n squared. What's making that so, as opposed to having an infinite amount of numbers?
We're going up to n only, right? We're summing from I equals 1 to n. And then at the end, we'll take n go to infinity. But we haven't taken n go.
Why do we have 3 right now as opposed to like plus 64 over n to the 4th?
So we just evaluated each of these sums.
Yeah.
Right? So like here, 16 over n, we have n of them, so we get 16.
No, that I'm cool with.
Okay.
I'm wondering why up here, like when we
Yes.
started off
Yes.
this, but we stopped when we got to the third, the 16 over I squared plus n.
Remember where this came from. This was the square of 2 plus 4i over n. Right? That's this term here.
Yeah.
Right? So what's the square of that? It's this. Right? What's the square of this? This is a plus b quantity squared. You get a squared, that's 4, plus 2ab, that's 2 times 8i over n, that's 16i over n, plus b squared, that's this.
Oh, okay.
Okay, that's it. So you don't have any more terms than that.
Hang on. Okay, cool.
Okay. Okay. So what happens as n goes to infinity? What do you get as n goes to infinity? Well, what happens here, you have n squared plus 1 over n squared, 64 over 2. What happens to n plus 1 over n squared as n goes to infinity? Goes end up as
1 over n.
1. Just 1. Right? Because n plus 1 over, right? n plus 1 over n squared tends to 1 as n goes to infinity. Right? So this thing turns into 32. This thing stays at 16, you have 32 here. And what about this? n plus 1, 2n plus 1 over n cubed.
Same thing.
Well, you're going to get, that will converge to 2, right? So you end up with 64 times 2 over 6. So that turns out to be the number that you get. Okay. And I think, actually, Mariah, I'm afraid we probably don't have time to do this for the second one. But if you do, it's just the same sort of thing. And magically, you're going to get the same thing. Okay. You actually end up with the same thing as n goes to infinity.
So with the n's, would you plug in like n minus 1?
Yeah.
Okay.
So you just put in n minus 1s everywhere. But as n goes to infinity, you're going to end up with the same number. Exactly.
Okay.
Yeah.
Believe you.
Yeah. I mean, what you said is exactly right. Right. You end up with when you plug in the n minus 1s, it all, as n goes to infinity, well, you're still going to get 1 here. You're still going to get 2 here. Claire.
Why does n plus 1 over 2 go to, or over n squared go to 1?
You should know this, right? Here's n plus 1
Oh, I see.
over n squared. As n goes to infinity, right, this thing doesn't matter so much, so you end up with 1. Right? Or you divide top and bottom by n squared. Right? 1 plus 1 over n, everything over 1. Right? And then as n goes to infinity, you end up with 1. Okay.
Wait, does this prove the definition?
No,
It's just an example,
this
right?
is just an example. Yeah. So here is one function. Here's one function So yeah, let me make this completely clear. What we said was that if your function is continuous, then it's integrable. That is to say, when you take your Riemann sums and choose whatever points you feel like, as n goes to infinity, you're always going to end up with the same number. Okay. And here we've sort of seen that that happens, right? We said, well, what happens if we take the right endpoints? We end up with this number. When we take the left endpoints, we end up with this number. In fact, if you chose any number, like if you chose some sort of random number, you're still going to end up with this number. Okay. And that's because your function is continuous. Okay. So it's just sort of giving you some sense that you actually do end up with the same number when you do this thing. Okay. Okay. So now comes the best part. So this process is in general, okay. Right?
Yes.
As you see, it's a pain.
Yes.
Right? It's a very, very difficult pain, but fortunately, we don't have to do it.
Yay!
We do the quiz and
We don't have to
Put
do
on the
it.
final. Maybe.
You might have to do it on the final. Okay. So here is what is called the fundamental theorem of calculus. And it's usually called the second fundamental theorem of calculus. Okay. So it says this: if f is continuous on AB, so you don't have to do it if we can find an antiderivative. Okay. So here's the second fundamental theorem of calculus. It says if f is continuous on AB and capital F is an antiderivative of f on AB, then in fact the definite integral can be obtained just by evaluating the difference of the antiderivative at the endpoints. That should be really shocking.
Again, the last part of this.
The definite integral equals the difference of any antiderivative on the endpoints. So here, for example, this turns out to be 283. Okay. This thing that we calculated before turns out to be 283. If we look at the definite integral from 2 to 6, okay, the theorem says find an antiderivative. Well, what's an antiderivative of x squared? X cubed over 3. So x cubed over 3 is an antiderivative. And the theorem says all you need to do is take x cubed over 3, evaluate it at the endpoints, and take the difference. Right? Take your antiderivative, evaluate at the endpoints, and take the difference. Right? And lo and behold, you get 216 over 3 minus 8 over 3. 208 over 3. So this should seem like a great miracle has occurred. Yeah.
You don't need to see.
Could be any antiderivative.
Okay.
If I add on 2, well, I'd just be adding on
Well,
a 2
it's just
here,
the
and I'm
difference.
subtracting off
Okay.
a 2 here.
Yeah.
So it doesn't matter. Any antiderivative will work. You don't need to throw in constants because they will cancel out anyway. Okay. So great, right? You don't need to take Riemann sums, the nth Riemann sum, and then let n go to infinity, and see that any choice of sample point, will end up with the same number, blah, blah, blah. As long as your function is continuous and you can find an antiderivative, all you need to do is evaluate the antiderivative, the difference of the antiderivative at the endpoints. Okay. Once I was having lunch with my postdoc advisor, and he said, if you could plagiarize any result throughout history, what result would you put your name on? And I said, the Calderon-Zygmunt decomposition. And he said, you are thinking too small. I would put my name on the fundamental theorem of calculus. I was like, oh yeah. Yeah, you're right. Okay. Okay, so example, just we'll do 1 or 2 examples. Here's one. Okay, here's one. Like the integral, the definite integral from 1 to e of 1 over x dx. Okay. Half of you can do it the Riemann Sum way, and half of you can do it the other way. No, I'm just kidding. Okay, so let's do it using the fundamental theorem of calculus. Right? What do? You find an antiderivative. Well, what's an antiderivative of 1 over x? ln x, right? So you take natural log of x, and you evaluate the difference at the endpoints. This is the notation one uses. When you write this sort of thing, you mean you evaluate it at this point and subtract the value at this point. Okay. So this is natural log e minus natural log 1. That's to say 1 minus 0. So the answer is 1.
So then that's the area?
That's the area. That's the area from 1 to e under the curve 1 over x. This area is 1. If I said, say, the integral from 1 to 4 of, no, the integral from 0 to pi over 3, secant x tangent x dx. Does anyone know the antiderivative of secant x tangent x? Victor?
Is it not tangent x?
It's not tangent x.
Isn't it secant?
It's secant, yeah. So you take the secant function and you evaluate it at the points. I'm sorry, this should be 0. Right? And you end up with secant pi over 3 minus secant of 0, which turns out to be 2 minus 1. Again, it's 1. So great, right? Fundamental theorem of calculus. It's really wonderful. Sometimes you can't always use it. You can't always use it. What's an antiderivative of x to the x, e to the x squared? There actually is no simple way to write down an antiderivative for e to the x squared. I mean, there is a way, but it's sort of a cheating way. Okay. So in this case, not so easy to. You can't really use the fundamental theorem of calculus. Okay. But if you can find an antiderivative, then you're good. Okay. So we'll talk more about this stuff next time. If people can stick around, I have homeworks to return, but if not, that's okay. Or